Hello, everyone. Welcome to this Open Neuromorphic stream. We're in my current living room. I hope you believe me. Today we have as a guest Brad Aimone. And I'm very happy to have him here because I think he has some very interesting opinions on where neuromorphic computing is going to go in the near future. Going to bring him up on stage right now.
Yeah.
Hey, Brad, how you doing?
Good. How are you doing, Gregor? Thank you,
Yeah,
everyone.
very good. Very good. Thank you. You got a nice setup there. Is this in your office?
Yeah, this is my home office here in Texas. I work from home, and
Really
a
good.
little bit messy bookshelf at the moment. Yeah.
Can you maybe introduce yourself a bit about? Yeah. Please go ahead.
Yeah. So I'm a neuromorphic computing researcher at Sandia National Laboratories, based out of New Mexico and Albuquerque, but I live in Texas and work remotely. I'm actually a neuroscientist by training, theoretical neuroscientist from UC San Diego, and I've worked a long time in neuromodeling, but increasingly neuromorphic computing has been the sort of focus of my work and our group's work, that, especially looking towards the algorithm side, the computing side, try to, where do we see how this technology can be impactful both in the near term, with systems that we have today, but also looking forward 15, 20 years from now. What does a more brain-inspired computing platform look like, and what are we going to do with that? So kind of fun to have foot in both the present and the future. It's a fun opportunity, fun time to be in this field doing that. So.
That's really fantastic. I think we had an interesting talk also the other day about focusing on not just the mainstream, let's say, deep learning approach to neuromorphic, like just taking from deep learning and then just applying them to spiking neural networks, but really trying to use these really bio-inspired approaches to do something that conventional deep learning cannot do. And I feel like you also go into this direction of you look for really new algorithms that are not necessarily just porting deep learning, if I may say so. So I think that's quite interesting. I think that's also where Fugu comes into play. Is that right?
Yeah, absolutely. I think, there's certainly a lot of interest, of course, in deep learning. I mean, it's been amazing the last, few years just in general, as well as the neuromorphic kind of mappings of it. But, I think there's a lot the neuromorphic has to offer, both in terms of computing in general, beyond just artificial intelligence, but other applications. And that's where a lot of our Fugu work is looking at is, what else can neuromorphic as just a new type of computer architecture impact? And then as well, long term, the brain is not doing deep learning. The brain is doing something far more powerful, far more efficient, far more dynamic and effective. And I think that's where we have to kind of keep an open mind as we're thinking about deep learning, as we're thinking about neuromorphic, where things make up. So it's kind of, there's a lot, and I'll talk a little bit about it in a few minutes about where we might go with neuromorphic algorithms. And by all means, we should be chasing neuromorphic and deep learning together. But a lot of the stuff we focused on, what I'll talk about, is looking in a little bit different direction.
That's really nice. I'm very much looking forward to the talk. With this, I'm going to leave you the stage. And if there's any questions, feel free to post them on our YouTube channel, and I will forward them. Organize them and then forward them to Brett. So please go ahead.
All right, well, thank you very much, Gregor, and thank you everyone again for the opportunity to present today. So as we were talking about a minute ago, I'm going to talk about Fugu, which is a open source tool that we've developed at Sandia National Laboratories and been working on over the last several years, looking both at a cross-platform, kind of intermediate representation by which we can program neuromorphic systems as they're coming available, but also looking beyond, like we were talking about just a second ago, moving beyond deep learning and looking towards a broader set of scalable algorithms and where we may go with that. So I'll give a little bit of context in the first few minutes, just in how we view neuromorphic algorithms, and then go into detail on Fugu and a few of the other open source tools that we've been working on the last few years. So I'm going to start off with the thank you slide, because there's a fairly large group of people that we have at Sandia and beyond Sandia. Not everyone, all of our collaborators are on here, but I'm not a computer scientist, and so I'm not a device physicist. I'm a neuroscientist by training, and so we have a very broad team of people that are involved in this, and so I want to give them credit from the start. And I think that we have to keep in mind this is an interdisciplinary field. We all have different views of the brain, what neuromorphic computing is, and by bringing those views together, I think we can do some really great things. So I just wanted to start with that. So just following on that, we all have this idea that the brain is going to give us great computing. That's why we're on this, they're at this talk, we're on this field. We all mean different things by that. If we look at whether we're talking about algorithms, things like deep learning, things like AI in general, or if we're looking at neuromorphic hardware, whether it's spiking chips or resistive memories, we can't allow these fields to kind of go on independently. They have to be thought of as both taking inspiration from the brain and working on them together, and that we actually need to forge ahead in a cohesive, strategic manner by talking back and forth across the more computer science, theoretical neuroscience side, as well as the engineering, device physics, computer engineering, architecture side. And if you look kind of historically, I like to have this sort of view that we're in the middle of this sort of transition of neuromorphic computing from kind of a conventional modeling brain-like things like deep learning on conventional things like GPUs and CPUs, and we're moving towards this sort of unknown future of what neuromorphic hardware may look like in 3 dimensions in highly complex, brain-like models that we don't even know enough about the brain to do today. But that's okay. We're kind of in still an early stage of this transition. And I have a dotted line on this figure, which I think is where we're at now, where we have these large-scale neuromorphic systems, things like Leahy and Spinnaker and the second generations of these, and True North came early days, and brain scales, and a lot of these platforms are very powerful and very exciting, and sort of the natural thing to do is say, well, we can put deep learning on these, and I think there's been some great work in doing that. But I think they also open up the door for what new algorithms may look like, and I think this is a step in the direction towards this future we want to go as a field, and it will look very different 5 years from now than it looks today, and that's okay. But I do think that kind of taking appreciation of what we have now and what we can do with it has a lot of value. So one of the things that I find useful to kind of set the context is, what do I mean by neuromorphic in this talk, in this conversation? And I think this is the sort of model that's kind of described here that we've worked with and kind of we view neuromorphic architectures as at Sandia. We see the sort of core primitive, the core programming element, the logic unit, as the leaky-integrate-and fire neuron. It's event-driven. It sends out spikes when things cross a threshold, kind of basic model that people are familiar with. And of course, there might be some extra capabilities. Maybe these are graded spikes or what. It doesn't really matter. And then a given chip, a core, consists of many cores of compute cores. And those cores have responsibility at a hardware level for hundreds, if not thousands, of these neurons and their connections. Each chip might have a few hundred cores, dozens to hundreds of cores. And that allows us now to scale up to getting to thousands, if not hundreds of thousands, maybe 1 million neurons per chip. And we can, of course, assemble these chips together in large populations of boards and so forth, where you can actually start approaching hundreds of millions, if not billions, of neurons in a single neuromorphic system. This is very exciting. This is kind of shaping neuromorphic in a way that's consistent with how we have viewed parallel computing over the years. And it's allowing us to get to scales that are more brain-like. We're not talking about a few dozen neurons on a chip anymore. We're talking about billions. And many animals are kind of capped out at 1 billion neurons. Humans are still a few orders of magnitude beyond that, but that's okay. We're getting there. I'll talk about this in a minute, but we view neuromorphic as a graph. Programming neuromorphic is programming a graph of these leaky-integrate-and fire neurons and the edges between them. they can be assembled in layers like in a neural network, but they don't have to be. And I think this opens a, thinking of neural networks as a special case, as kind of a restricted case of this, as opposed to the end case is very useful, I think. Why we're thinking of it this way is at Sandia, we have been fortunate through a lot of our funding through Department of Energy in the US to build a test bed of very large systems. So we are expecting, right now we have one of the largest Loihi-1 systems, 384 chips. We have a number of Loihi-2 systems. We have a Spinnaker board. We've played with True North through our colleagues at Lawrence Livermore. We are expecting in a few months to have a billion neuron Loihi-2 system set up, and it's kind of, we think at the time will be one of the biggest neuromorphic systems in the world. We've been talking with the Spinnaker 2 folks. We have a Spinnaker 2 test bed. So when you're looking at, in your lab space, a billion neurons, and you start thinking, what do we do with this? It kind of changes how we actually want to program these things and what it means to program them. So what we really are paying attention to is we're going to have a graph of neurons. We're going to have a billion neurons that we can assemble into any compute graph we want. Maybe not any, but of course, much bigger than much broader than we think of today in terms of neural networks. What does this mean? What is the sort of software stack? What's the theoretical computing frameworks that we want to use? How are we going to get I/O? How are we going to deal with that? What are the applications we're going to target? These are all open questions. They're very exciting questions to be looking at, but at the same time, we can look at neural networks in AI. We can look at large-scale graph HPC systems and HPC programming models from other places, and we can take things from those fields, but we also have to develop our own solutions. So, again, not to sort of belabor this point, but we really are, the first thing I guess that's important here is neural networks are a special case that may not be the best fit for this. And I think we have to have an open mind to that. If we can get neural networks to go well on these large-scale spiking systems, that's fantastic. And we've done some work in this area. Other people are doing tremendous work in this area. But the computer architecture low level is more what you see on the top. It's a graph of arbitrarily connected neurons. We can program anything on these things. It doesn't have to be, feed-forward linear algebra things. And my intuition is it probably will be better if it's not. We can take advantage of learning and time and dynamics in a way that today's AI isn't really doing yet. And hopefully we can influence where AI goes as a community, which will be a challenge. But I am open to that, kind of possibility. I think we all should be. So nonetheless, we're seeing in this case where we have a lot of neurons now on our neuromorphic platforms. We have a lot of neurons in our brain, a lot of neurons in our AI algorithms. They're all different. And I think this is, this sort of appreciation it's not just can we get to these scales? We're at the right scales, but scale isn't everything. I think this is going to be, a simple little takeaway message. It's obvious when you think about it, but at the same time, it's worth kind of acknowledging. Okay, so specifically, what algorithms are we thinking about? And I've mentioned, of course, there's neural networks. We would like to get to the things you see on the right here, where you have more brain-like algorithms. I think this is a hippocampus circuit, kind of inspired some work I did many years ago. And then there's things like what you see on top, where we're looking at work that we've done in recent years, looking at Markov chain, Monte Carlo, Strawson multiplication, a number of other probabilistic models, graph optimization things. And these are very disparate types of use cases for neuromorphic. And I don't think one is better than the other. I think they're all part of this sort of manifold of algorithms that might fit on this architecture. And this is something that we want to make sure our tools are, maybe no one tool is going to cover everything, but we want our tool or assembly of tools or community of tools to cover the space. So, like I mentioned, we have these three broad categories, kind of a broad brush, where we have neural networks. Everyone's familiar with these now. thing we'll call spiking neural algorithms. These aren't going to be necessarily things like deep networks. These might be arbitrary graphs. They might be graph algorithms, or we call them artisan networks sometimes. And then we have things like really brain-inspired stuff. We don't know this bottom category here. We haven't gotten there yet. We would like to get there in the future. We're working towards that. But I think, these are very, this is kind of building on classic computer science. This is building on AI. We have a little bit more runway here, so we know more what to do on the top two. And then there's the flip side, which I'm not going to talk a lot about when we get to Fugu, but I think we have to acknowledge, which is the hardware is changing very rapidly also. So we have this dynamic and ever-growing landscape of algorithms, but we also have this incredibly dynamic and flexible landscape of hardware platforms at the same time, where people are adding learning and analog and non-silicon devices and stochasticity and coin flip devices, which is something else I work on. We don't know what our hardware is going to be in a few years. So how do we deal with all of these algorithms and all of this hardware changing at the same time? And so this is where we really want to think about software tools that facilitate kind of a stable representation or a stable level for algorithm design that's flexible both to the applications changing as well as to the hardware underneath changing. And this is, we're not alone in identifying that you need an intermediate representation for neuromorphic. There have been some amazing works with the, our approach that came out on Archive a few weeks ago, and other people have been looking at this. We have a little bit different focus, as you'll see, which is looking more at the straight computing applications, a little bit less of the AI, but nonetheless, I think we need to focus on this transition here. So, my colleagues, Craig Vineyard, William Severa, and I, we were sitting in our lab, which is not quite this fancy, but I stole this picture from a video a few years ago. And we were sitting around kind of early days, I think, for us in this area, where we're like, we're going to get these, big Loihi platform at the time. And we were thinking to ourselves, what does it look like to program that? And we threw on the whiteboard. We just had a whiteboarding session for a few days, and we really were trying to come up with this idea, and we recognize that this idea of an intermediate representation is needed, and that we've called Fugu. And the idea, what's on the whiteboard is not that important, but it's that we recognize that you're going to have use cases. This is obvious to computer scientists, but to someone who's not a computer scientist like myself or the neuromorphic field, it may not be. The people who ultimately are going to use neuromorphic hardware aren't going to know anything about neuromorphic hardware. They're not going to think about how to program things in neurons. They're not going to think about, how to draw a synapse between one node and another in a graph to convert some information. They want to have a library of functions that they can program out of C or Python or MATLAB or Fortran or whatever it is they use, and just call it and say, I don't want to use the GPU for this. I want to use a neuromorphic chip for this. That's the level that they want to work with. Meanwhile, you're going to have people like myself, who's maybe more on the neuroscience side, thinking in terms of neurons and synapses. It's fine. I love coming up with algorithms of neural circuits that do things, but I don't really want to think about how to move shift registers from one thing to another on, under the hood of an ARM core or a Loihi chip or a True North or whatever, or programming a memristor or whatever it may be. But then you have the neuromorphic experts that want to work at that level, and they don't necessarily want to think about the algorithms, and certainly they have no idea what the applications may be at the very high level. And so we need some way to transition between all of these. So this is where we have Fugu, and we want, I'm going to stick this up later, but this is why we put Fugu together, and we want you as a community to contribute to this. So I'll put the slide up at the end, but I just wanted to, for some reason, stuck it in here to sort of remind people this is out there. We want to work with you. So Fugu is meant to be this sort of tool to facilitate this vertical translation of neuromorphic bottom up and top down. knowing that the hardware is going to be changing and the applications are going to be changing. And the idea is that we have an open source library of these spiking neural networks, spiking neural algorithms per se. They don't have to be deep learning, they can be. We want the intermediate representation to be as hardware agnostic as possible and flexible to enable future mappings to future hardware systems. We have two kind of core concepts of representations. We have bricks, which you see here, kind of as these are, you can think of this as the library of functions. These are the sort of pieces by which one would actually represent have a set of neurons that represent some computation or function. And you have a scaffold, which is kind of the program that assembles those bricks together, the program that pulls together functions from a library to do something. And then we have backends that actually will map it onto whether it's Loihi or Loihi2 or Spinnaker, Pine, pardon me. This and all of these things can be extended, and we hope will be extended by the community and by ourselves. I'll start off by saying what Fugu is not. And I've said a little bit of this. Fugu is not a deep learning tool per se. We're not trying to compete with things like SNN Torch or Whetstone or any of these other tools that are actually trying to map Slayer artificial neural nets into spiking. We want to take advantage of those, but that's not the goal here. Similarly, Fugu is not a neurobiology modeling tool. This isn't Brian. This isn't Pine. This isn't Nest. It's not trying to model. If someone has a brain-inspired model they want to simulate, those are the tools you should use, not Fugu. Again, if someone has a module that's based on those tools, we would like to be able to import that into Fugu and use it. Fugu is not a replacement for the software stacks for a given hardware platform like Lava. And Lava has a lot of the capabilities that we want to be able to work with. And we've talked to the Lava people about integrating Fugu in with that. So it's really meant to complement these different layers. It is an intermediate representation that should allow efforts that are occurring across these scales, as well as things that may not be represented by these existing tools. And that's why I focused a little bit on these spiking neural algorithms that I've mentioned a few times, and be able to bring them together in a way that can make them usable to people with different levels of expertise. Okay, so I'm going to go through an example of how Fugu works. I'm actually going to pick a machine learning type kind of example because people are familiar with that. And then I'll go into actually what these bricks look like in a few minutes to give you a better idea of what actually is going on. So the idea of Fugu is that I'm going to have a library of bricks. These bricks are going to be functions that are describe a neural circuit. They're not hard-coded neural circuits per se. I'll explain why in a minute. But they'll basically have some sort of, their scripts, Python scripts that will actually describe how to build a neural circuit that does a given function, like a dot product or a convolutional net or liquid state machine or an adder or a whatever, a winner take all, whatever you want. You can think of them as like a functions or data flow bricks, what have you. I'm going to compose a scaffold. This is my program where if I'm building a liquid state machine, I might have an input layer. I actually have a liquid per se, and then I have a linear readout layer, linear regression readout layer. The sort of computer science user, machine learning expert, so to speak, doesn't know anything about neuromorphic, just says, I want to use these pieces together. Not all that different than how you might go into Keras or PyTorch and say, I want to take these blocks and assemble them together into my, my data flow pipeline or whatever. Fugu does all the connections and the managing the links between these things, and it composes the sort of larger neural circuit out of this. I can then, if I say, no, I want the input to go into a convolutional layer. Instead, I just describe my scaffold that way, right? And I'll show you an example of this in a few minutes. Currently, these scaffolds are directed acyclic graphs, and the bricks, the bricks are full neural circuits, and I can assemble them however I want out of neurons. So these can be cyclic, arbitrary graph structures inside the bricks, but the scaffolds have to be directed acyclic graphs. And we currently use, everything is kind of done on a network X layer sitting on top of Python. And that's where we kind of get our DAG constraint over here. You can do all sorts of weird little things, right? You can do splits. You can work with delays, and Fugu handles a lot of this sort of idea that if I want to compose something which is maybe not maybe has some sort of parallel computing pathways and bring things together, it can do it. After I write the scaffold out, then I want to actually I do the brick laying, so to speak, to kind of follow the metaphor. But I actually build the neural circuit using the brick instructions that actually builds the population of neurons, leaky-integrate-and fire neurons, that represent this broader algorithm. And Fugu will also add a number of control nodes that will keep track of timing and synchronization or whatever it is that I might be required to do for my given application. We call them control nodes, control neurons. I got a question here on, are there Fugu use cases run on HPCs? So yes and no. So Fugu is designed, ultimately we want to run it on neuromorphic systems. Like I'd consider like a billion neuron Loihi2 system and Loihi2 HPC, and that is our goal. We're working towards that right now. We are mapping algorithms that are generally used on HPCs, like stochastic differential equation solvers that leverage Monte Carlo random walks. We have been developing neuromorphic algorithms for those that we are putting into Fugu with the hope of actually getting those onto the sort of Loihi2 testbeds we have. We're not currently running Fugu. Fugu will do a conventional simulator. That's kind of one of our backends. We are mapping those onto GPUs. We currently don't have a need to go on to HPC systems to actually run simulations of our Fugu models yet. But it is something that we could do. Okay, so Fugu builds a graph of neurons on network X. So now network X is actually a graph of nodes where the leaky-integrated fire is each node, and the edges between where the synapse between the neurons. This graph is platform agnostic. The idea here is that that graph should be the same graph that I would put on Loihi or Spinnaker or True North, Brainscales, NeuRAM, whatever, right? Eventually, you come up with a new neuromorphic platform, you should be able to use the graphs that come out. It's just leaky-integrated fires with edges. If I change the size of my input layer, the scaffold in Fugu should handle the rescaling of this graph to accommodate that. So basically, these bricks aren't hard-coded. They should be scalable based on my program. So if I'm running a fast Fourier transform and my vector's length 100, and I build a little Fugu scaffold to do an FFT, but I then decide I want to rescale that to do something with a size of 1,000,000. I shouldn't have to rewrite anything. Fugu should automatically take care of that, and that's what it does. If we compile Fugu, when we can do the compilation step, this is when it goes to a backend. The backends are hardware specific, platform specific. So this graph, in this sort of generic neural graph that we have formulated here, is kind of, it doesn't make any assumptions about restrictions on fan-in or any, delay precision or whatever. But if I go to hardware, as we know, every different hardware platform has its own precision constraints. It has its own timing constraints. It has, different fan-in constraints or number of neurons per core, blah, 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 blah. That's the responsibility of what we're calling the backends of Fugu to handle that sort of mapping. It basically equates to taking this sort of intermediate representation graph and adding neurons or merging neurons or whatever it may be to make it something that will fit on the platform. And that's the responsibility of whoever writes the backend compiler. We have a couple of those that we've written for, like I said, Loihi and Spinnaker 1. And we're working on one for Spinnaker 2. but it's certainly something that someone might come up with an idea that you have this generic intermediate representation, and if you have some neuromorphic platform, by all means, we would love for you to write a backend that goes from Fugu onto your hardware. That's fantastic, right? Fugu then will deliver this to the hardware and execute it according to however your system's configured, and will run the inputs and outputs and process. And we don't have beautiful viz or UI at the moment. It's something that we're of course, like everyone else, always thinking about. But Fugu handles the data management through the algorithm, through the platform. So I'm going to give a concrete example of what Fugu code looks like on something that I wrote. You forgive my computer science, my Python skills, but this is actually a use case of someone who knows neural algorithms writing a Fugu brick. This is a paper that we published at ICRC a couple of years ago on streaming neural binary arithmetic. The idea here is not to change how we do math. Of course, you're going to use a CPU or GPU to do that, but it's to illustrate what you can do with neurons, where we want to actually add binary numbers and build neural circuits to do this. And so just a very brief context, if you're familiar with binary representations of digits, you typically will see it in this form, where you have the most significant bit first and the least significant bit last. What we realized a number of years ago is you could flip this around. You take your least significant bit first, little endian representation, and then you do it over time, and that spike train basically represents your digit. So the 13 is represented by the ones place, the 10th place, and so forth, then binary going forward. And this makes it that I always start with the least significant bit, so my encoding scheme is length agnostic in some sense. I just, as long as I'm providing numbers, zeros or ones, I can encode higher precision numbers. Not to belabor the particular merits of this, but we can do some interesting little neural circuits. And so this is an adder that takes advantage of this coding scheme. I take two inputs that you see on the top here. I feed them into a graph that looks like this. I have two different neurons representing kind of carry bits in a sense. This is implementing binary addition. It's the same you would do if you built a digital circuit, but instead of having a digital circuit to do this, I'm able to use neurons that have delays and different weights. And I can get by with 3 hidden neurons actually allow us to get a sum of 2 streaming binary digits. And this figure is not super easy to see, but what you can see is kind of a video. Spikes come in, they take turns inhibiting and delaying themselves, and that will actually allow me to get my streaming ad. It's a cute little algorithm. This is what we call an artisan algorithm. It's kind of handcrafted to do exactly this. It's not very scalable per se. You're not going to try to do tremendous things like this at large scale. But if I have the ability to add in neurons, I might want to use this as part of something bigger, right? That's the idea of Fugu. So this is actually what a brick looks like in Python, written out to do this circuit. And what you can see is there's a lot of control code and sort of boilerplate things that describe what a brick is. I define my control, my beginning and end neurons that you don't see on this plot, but you saw that kind of says, okay, I'm starting my encoding and I'm ending my outputs. And then I actually define the edges and the nodes. So here I define 4 nodes, the 3 hidden nodes and the output node, label them as I want. I write the edges in between my inputs and these nodes. This is all network X formatting. And I end up having my edges between the control nodes that aren't shown in this diagram here. And that's my brick. And now I can use whatever adders I want for whatever I want to do. So this is a scaffold now. So if I'm writing my program and I say I want to have a brick that does addition, I add my I say these are my inputs, these are my 2 digits. I have my adder, I'm using input 1 and input 2. And I define what my coding schemes are, so it kind of just knows what's going on. And then I hit go, and I compile it onto whatever my backend is. This is the simulator. And it'll spit out, neuron whatever fired at these times. So this is the basic idea of what a Fugu brick and probably the simplest Fugu brick and the simplest Fugu program in a scaffold would be. But to kind of show what you can do, we've actually done these cases where you can start assembling these adders together with delays. A delay effectively is a multiplied times 2. In this coding scheme, it's just shifting in time. It's effectively waiting, having a 0 in front of your little Indian coding. So it's multiplying times 2. So combining these multipliers and these adders, I can multiply any two, a scalar times any number. If I have an inverter brick, which you can do, I can then do subtraction. You can see how you build up to basically a arithmetic logic unit of neurons. It's not something, of course, this is far less efficient than using transistors. I'm using these neurons that are made of thousands, if not hundreds of thousands of transistors. But it just shows that we can do it. And it kind of points to how one can assemble and compose more complex things. On our GitHub, there's an example of a Fibonacci sequence where we actually build out, simple Fibonacci code in this way, which is, that's the Fibonacci scaffold. Take an adder, take the output of one adder and add it to the next, one of the inputs plus the output of the adder, and you get the next output, and so forth. And then this just gets higher and higher resolution to the Fibonacci numbers. This is all, we've done this on the Leahy. It can go as long as I want to wait. So you can kind of go arbitrary length Fibonacci if you want. We can also do this on, recursively. Kind of that's the beauty of Fibonacci as a recursive algorithm. And I can actually build a brick now that's not a scaffold of adders, but rather a brick that actually has this feedback loop in there. And it does the same thing. It's computationally equivalent. Much more compact, fewer neurons, and reusing the same neurons over time. So we're programming in computer science way on neuromorphic hardware now by using Fugu. So, that's the basic idea of Fugu. I'm going to go through one final quick example of where we're thinking of going with it, beyond just the sort of adding bricks or by hand and working on backends. This is work mostly William Severa has been leading, where, if you want to sit there and custom write an adder out of neurons, great. But what you probably want to do is actually use something, take advantage of learning, whether it's machine learning or things like genetic algorithms, to actually write these bricks for us. And this actually is a use case where we might be able to use HPC to take advantage of the sort of raw compute horsepower to actually explore neural connectivity space to do this. So William and colleagues have been using evolutionary algorithms. They have focused on using NEAT, which is a neural network evolutionary algorithm approach, where we work quite a bit with Katie Schumann and her crowd at University of Tennessee on EONs as well, looking at how we can use that for spiking neural networks and going to Fugu. So the idea here is that you couple into this sort of Fugu framework the idea that I actually want to explore and develop different neural circuits that might do this. So NEAT basically kind of gets this thing that we want. It's like, can we come up with neural circuits that might build a little neural network, a little small bite-sized network that allows us to define a brick in the sense that solves, helps us solve our problems in a way that we may not know what it looks like to start with. So what's, of course, all these tools are in Python. They're all, in some ways, it's not that hard to make them cross-compatible. And so what William and colleagues have done is they actually had a ability that you, in a sense, can actually, incorporate a lot of generations of neat, kind of neural circuits within this sort of Fugu process. And so Fugu then will assemble those different, children of the genetic search and search through them and kind of work with the evolutionary approach in order to understand what might be the best approach, a best solution. In a sense, building a brick custom for my application that I need. So I won't go through the exact example. It's just kind of, this is a fun video that they had where they were able to, you can see sort of that each generation gets a little bit better at this particular function, which I'm of course blanking on exactly the one they were looking at here. But this optimizes over time through generational searches in what our actual neural circuit can be. So this is a nice example of how Fugu can actually take advantage of things like NEAT or EONs. You can do the same thing with neural network training, where I'm going to build, the bricks will be something that is learned or kind of adapted to as a, part of a search process. And they've done this for a number of things. For sake of time, I won't go into a lot of detail on these, where they're looking at, simple machine learning cases or XORs and whatnot. So they do signal processing, where you actually use the sort of sparse projection, a neural circuit that kind of broadens this out, takes a time signal, does sparse projections of that, and then you have the NEAT does a search over that, and it works out. So one of the goals is that when we're looking over searches of these sort of neural spaces, we need to start using the neuromorphic hardware to accelerate our search, because neuromorphic hardware, of course, is designed to run fast on things like large graphs of neurons. And so we are running into cases where we're running into cases where the processing time is taking a long time on things like genetic algorithms. But now compile times are starting to be the biggest constraint when it comes to things like leaky. So they're asking the programming languages for Fugu. Fugu is entirely Python based. We did talk a little bit about whether we should have it in C or Python, but of course the world is in Python now, especially machine learning, and it allows us to take advantage of things like NEAT and EONs and other tools that we can have them interact with, as well as the many other tools that Neuromorphic is developing. It is, at the moment, highly dependent on Network X. So Network X, if you're not familiar with it, is a Python library for describing graphs and doing a lot of basic graph analytics. It's basically a dictionary-based approach to representing graphs in Python. So Network X, I think, is quite effective for Fugu at the scales we've been using it on. Ultimately, if we want to go to really large-scale circuits, billion neuron circuits, we very likely may need to move away from Network X, and we may need to move away from Python, to be honest. But at the moment, everything's Python and Network X, and there's no other really strong dependencies. Okay, so that's the idea of Fugu and NEAT. And in general, I think where we're going a lot with our Fugu work. And before I move on away from Fugu, I do want to throw these QR codes up there. The one on the left is actually where you can get to Fugu and get in GitHub. Of course, just search Fugu and Sandia and it'll show up. And we would very much, like I said, like for people to work with us on this. I do want to very briefly talk about two other tools, just kind of in this sort of mindset of how things are fitting together and how Sandia is trying to fill some of these gaps in the sort of compute software infrastructure on Neuromorphic. And specifically, when I talk about stacks and N2A, these are tools that are more focused a little bit on the neuroscience constrained algorithms. And they're meant to work with Fugu, actually. So the first one is called Stacks. Stacks is a program is developed, led by Felix Wang in our group, which really is similar to things like Nest and Brian, which is focused on large-scale neural simulations, more biologically inspired simulations. This is actually an HPC-focused tool, in some ways similar to Nest, where the idea is that, if you're doing simulations of biologically realistic scales, you're going to want to probably go to, many cores, many nodes, especially if you have a lot of long time scale simulations, which many biological models tend to be run only over a few seconds, but of course cognition exists over days and weeks and months, right? So we need HPC for this. The tools, there are a few tools out there that we thought there could be more. So Stacks is a tool that is meant to kind of take advantage of asynchronous communication of neurons over large populations and HPC systems. That's based on the Charm++ parallel programming paradigms. So we've done a number of things with Stacks. I think the biggest innovation is that it focuses on more gracefully parallelizing these large-scale networks across a highly distributed compute infrastructure. And so, biological circuits are not all-to-all connectivity. They're highly structured in their connectivity and their adjacency matrices. And so you want to somehow partition your graphs. And I actually think that this is something that's going to be particularly important as we look towards neuromorphic hardware and these really large-scale networks, whether they're Fugu-like, graphs, kind of generic graphs, or even deep networks. I'm going to have thousands of neuromorphic chips. How do I distribute billions of neurons over those 1,000 chips? And I think lessons we're learning in Stacks, thinking about how to port models into HPC systems, are going to be the same lessons that we need for porting, whether spiking neural networks or spiking neural algorithms onto large-scale neuromorphic systems. The embedding and parallelization and partitioning, all that's going to be critical, and it's very early days on this. We've done some, we're focused quite a bit on looking at how to analyze these large-scale systems. This is a process Brad Thielman, a postdoc in our group, has worked on something called graphical neural activity threads, how to process data coming off of this scale. We're going to deal with the same sort of thing on large-scale neuromorphic systems as well as large-scale simulations in HPC. So currently, Stacks is meant to take in inputs from things like N2A or Fugu. I'll talk about N2A in a second. And it can program, distribute these sort of large-scale, neural models and run them on HPC-like infrastructures, things like Sandia's supercomputers, Oak Ridge's supercomputers, and other places. And we're thinking about how to actually move this into things like robotics platforms as well. So this again is to kind of highlight that this is sitting in this intermediate part of this ecosystem. So the final tool I'll talk about for the last couple of minutes is N2A. N2A is a program that was started by Fred Rothganger at Sandia. You can go find it here on GitHub. It's called Neurons to Algorithms. This really is meant to be a more almost a neuroinformatics view towards kind of capturing the biological complexity that we know of from the neuroscience world, codifying that in a computable representation that one can then translate towards models. In some sense, now we're moving more towards the biology, away from the sort of neuromorphic. But how do you represent the complexity of the brain in a form that neuromorphic can take advantage of? And that's what N2A is meant to get to. You can look at things like, this is a Hodgkin-Huxley model. These are now biophysical equations that describe the dynamics of ion channels. But of course, these dynamical formulations is how the brain is working. This is how actual information is changing in the brain. And we would like to, hierarchically build up from that to the sort of algorithms that we have in Fugu, and vice versa. So Fred's done Fred's tool N2A actually is very efficient at mapping between these different levels of representing sort of biological complexity back and forth. It is a more dynamical view of how the brain works, is kind of codified in this, which is a little different from how in Fugu we're taking this sort of discretely key integrated fire approach, and it's very different from the neural network view. But in some sense, we're seeing these as kind of a part of a broader ecosystem. And I think Fred in particular is an advocate of the sort of open neuromorphic view of building up, this way we want to have bricks from everyone in the world. We would like to be able to have N2A sort of descriptions of how biological processes are evolving as well. So I encourage you to look both at Stacks as N2A as well as Fugu. Yeah, I'll skip that. So anyway, I guess just to kind of wrap up, we see these tools, particularly Fugu, Stacks, Intway, other things we've done in the past like Whetstone, but they're complementary to the broader set of tools that this community as a whole is putting together. I think it's very encouraging to see that all the progress that's been made on the spiking neural network front. I just threw a few up here on this slide. I suspect that there are another dozen that I left off of here, and I don't mean anything by that. Just I think it's exciting that the computer science side of Neuromorphic is beginning to explode, and I think it's I wish it had happened 10 years ago, but it's exciting to be happening now and to be part of that. And with that, again, just to throw up a slide of the people who did a lot of this work. I'm a neuroscientist, neuroalgorithms person. I am not a software developer, and so major kudos to all of those people and the people from all sorts of scales. This figure comes from a paper we had a few months ago, highlighting that we all look at the brain in slightly different ways, and we all see different things. But the only way we're going to make any inroads in doing this is by talking to each other. So with that, I'd like to thank you all for listening to me talk about it. I'm looking forward to talking to you all about how you see the brain and how you see all of this. And thank you to Gregor, Fabricio, and Jason for this wonderful series and the invitation to present with you all.
Thanks a lot, Brad. That was really interesting. Thanks a lot for that. I have a few more questions, if you don't mind. So there's a few intermediate representations out there, like Pine, and now we saw the neuromorphic intermediate representation there from a recent Telluride project. How does Fugu fit into that ecosystem? Can you say something about the differences maybe to them?
Yeah, absolutely. So I was going to put a slide in on that, and then I realized I had like way too many slides in this presentation. So I think I think all of these are important. And when I've talked to the NIR folks, and we've had some great conversations, right? I think it's very exciting, and I think their approach is a little bit more. I'd say they have a more continuous model approach, right? We're taking a very discrete. Our model is almost. I'd say it's almost inspired by True North as much as anything, right? It's kind of like, what is the simplest, most logic gate view of what a neuron is, and build an intermediate representation out from there. NIR has this, I think, very elegant approach, which is, here's a differential equation view of what a neuron is, and let's build out an intermediate representation from there. These are completely compatible. I think, they're kind of special cases of one another in some sense. And so I don't see any reason why, I would say we need both of them, and we need multiple of these. And what we need are ways to connect between them, because there are going to be certain algorithms, and we learned this actually, direct experience, learned this in working with some of our algorithms, like the Markov chain random walk stuff that people may have seen, where if you haven't seen the algorithm, the idea is that I have a mesh. At each location of the mesh, I have a number of random walkers. Each of those random walkers is represented by a spike, and a set of neurons delivers that spike according to some transition matrix to another mesh point. Really simple algorithm, really powerful algorithm for neuromorphic. That algorithm works really well on something like True North or Loihi using a Fugu type representation, because those models are those hardware platforms are very discrete, and they're very very synchronous in terms, they're asynchronous in some of their communication, but they're very synchronous in terms of how they handle time. When you look at things like Brainscales and Spinnaker, those hardware platforms are are more dynamical, especially brain scales, are very much more dynamical in terms of how the neurons are updating over time. They're solving differential equations at the hardware level, right? And so I think if we had the NIR framework 4 or 5 years ago, at the time when or maybe not that long, 3 years ago when we were doing the random walk stuff, it would have been the natural way to represent the Markov chain random walk work to get into brain scales, because brain scales is analog. It is evolving using these sort of dynamical differential equation frameworks. So that actually, I think there's a value that there's this sort of intermediate representation that's slightly different perspective that makes certain algorithms or certain hardware more amenable to work with. Pine, I think Pine is something that came out of the computational neuroscience world. It's a more neuroinformatics-based approach where you think about populations of neurons in the brain. Like, I got a population of CA1 neurons that receives inputs from a population of CA3 neurons. It's fantastic. We need that. It's a very different way of writing an algorithm than writing a neural network or writing a little adder like I showed. So I think these sort of community of intermediate representations is going to be a fun place to be in the next few years, because I think that there is a lot of places where we can work together and build on each other.
Yeah, I think I see. Thanks for your insight on that one. I have another question that's how to frame it. Like, machine learning is eating the world essentially, and I feel like neuromorphic is still trying to find its place. I mean, you especially looking into into a different approach of finding like different algorithms or constraint optimization or graph algorithms or signal processing. How do you see? I feel like we're a bit in a race. Do you think neuromorphic can find that place? How everyone is looking at machine learning applications at big scale at the moment, at least. Are we going to just find our niche, or are we going to actually improve the ML ecosystem? Or how do you see that?
Yeah, so I think this is an important question, and I don't know if I have the answer on this question, right? But I think this is the question we all should be asking ourselves. Neuromorphic, we disagree as a community. I mean, are we hardware people, or are we architecture people, or are we algorithms people? First off, right? And I think it's a little different if you're coming from those different areas. But I'd say that it's probably, in my opinion, it's probably a mistake to just say, what have people done on GPUs lately? Can I put this on neuromorphic today? Because GPUs are really good at what they're doing right now. They are exceptional. And we can talk about power all day long, but it doesn't matter if you're not going to fit whatever application onto your neuromorphic chips. It doesn't matter that you're low power if it doesn't fit, right? And ultimately, all of our neuromorphic algorithms and solutions are taking advantage of processing and memory at some level, right? We're taking some application and we're stretching it out and we're expanding it to fit the hardware that we have. And if you're talking about a large language model, GPT-4 or whatever, I'm going to need a lot of low-EHE chips to fit that at the scale of the current solutions. And I don't have von Neumann architecture there to help me, rapidly iterate through some big memory I have sitting on the side, right? So I don't think that we're going to win that race. I think that the race is, it's not the race that we should be in, right? Just in the same way, I'm not going to win the gold medal at the Olympics in anything, but in a sprint, right? It's just not going to happen, right? We just have to accept that and move on. But at the same time, there's a lot
No,
that
I
we
think
have to offer. That's what we should be focused on.
that makes sense. I think one question that I'm also like asking myself that is related is that I mean, even when trying to model the brain, like we're thinking of scale, like large scale models. However, so far in my experience, when it comes to asynchronous asynchronous computation, um, I haven't seen any benefits in like when scaling goes up. So maybe what I'm trying to say is, I think I've seen personally the benefits of some neuromorphic algorithms in small scale systems. However, as they are scaled to bigger size, it sometimes then at some point it's just more efficient to just do the synchronous clock computation because it's just higher throughput. So do you think you can comment on that one as well? Like even it doesn't have to be deep learning, right? But even let's say about some of the biological principles, does it actually make sense to scale them up in silicon? Maybe that makes sense.
Yeah, I mean, I would agree. I don't think we have not seen it yet, right? And I think that, but I do think there's a difference between we haven't seen it because there's no advantage, and we haven't seen it because we haven't found it, right? The hardware lottery, if everyone should read that paper, right? The hardware lottery biases are baked into everything we are doing. And it's like we have to actively be asking ourselves, did I accidentally think about my problem in some serial way that is forcing my hand and taking away the advantage of neuromorphic that I don't even realize, right? And I think that comes up in a lot of places, not just in neural nets. So I do think we need to be cognizant whenever we look at any application and say, could I have done this in a different way that makes it more scalable in the way you're asking? We're a long way from brain-like algorithms, and there's a gap between the computational neuroscience world and the neuromorphic field. I fully believe that we will see. I fully believe that in some point in the future, we will see brain-like AI algorithms that scale really well, and you gain benefits by using more powerful neurons in a neuromorphic sense to get scaling advantages. Because, I mean, there's an existence proof of that, right? The neurons in our brain are far more complicated than the neurons that we have in neural networks. And they're much more efficient in terms of latency and computational depth, right? You can figure out how to hit a baseball in 7 clock cycles in terms of neural clock cycles in terms of latency, right? From where the decision's made, from the retina to where the decision's made, it's like 7 layers of neurons. We can't do that in anything in deep learning today. But those algorithms, we don't have those algorithms yet that take advantage of having recurrent networks and complex dynamics in the neurons themselves and the learning at short terms and there's a whole list of things. So I don't know. I think there's a ways to go, but I'm convinced that we will see those scaling benefits at some point.
Honestly, that's very good to hear that from you. I hope that we can see that. I sincerely hope. Yeah, it would be nice if you can replicate that on a new substrate. That's bound to be seen. I would say. Brett, I think we're already over time.
Okay.
So I wanted to thank you again very much for your presentation. It was super interesting. This was recorded, and so it was live streamed on YouTube where people can share it. And so, yeah, with that, I would like to thank you again, and I hope to see you soon.
All right. Well, thank you. And anyone, feel free to reach out if you have any other questions. I appreciate the opportunity to speak with everyone today.
Perfect. Thanks a lot. Bye-bye.